Okay, so now we can talk about order of convergence. And before we go too far, let me at least remind you of the notion of linear convergence in the vector space setting. So a sequence xk, k goes from 0 to so on, of points in Rn is said to converge linearly. All right, to a point, let's call it x star. Okay, if there exists some constant c, which is contained in an interval from 0 to 1, and an integer k, okay, which is greater than or equal to 0, such that for all little k, which is greater than big K, we have the following inequality, which is that the difference between the x plus first point from this limiting point in norm, the difference of these 2 points, and then take the norm of this, is less than or equal to some constant times the distance between the cave point and x star. So more or less, it's like what happens is that the distance from a point, it's like to the limiting value, decreases by a multiplicative factor of c each time. Okay. All right. So to generalize this, to manifolds, right? One might be tempted to sort of do the same thing, but using local charts. Use charts to sort of make sense of this. But you don't get a notion of convergence that is independent of the choice of charts. So you can't really sort of pursue that route. Okay. So what you can, of course, do is that we've been working in the context of Riemannian manifolds, right? And on a Riemannian manifold, there is the notion of a Riemannian distance between points. And of course, this is in a sense a distance. One way of thinking about distances, it's like on Euclidean spaces between a point xk plus 1 and xk. So it's natural to replace that with a distance between xk plus 1 and x star, and here distance between xk and x star as well. And that's exactly what you would sort of ought to do. It's like if you have a Riemannian manifold. Okay, so if M is a Riemannian manifold, right, the induced Riemannian distance yields this notion of linear convergence. Okay, sort of the fairly obvious notion. Okay, so definition of linear convergence. Right, so let M be a Riemannian manifold. And let the distance denote the Riemannian distance. we say that the sequence xk, k goes from 0, 1, and so on, converges linearly to a point x star on M. Okay, if there exists a constant c in the interval from 0 to 1, and an integer k, right? So we're just mimicking sort of what we had before. K greater than or equal to 0, such that, right, for all little k greater than or equal to big K, we have that the distance between xk plus 1 and x star is less than or equal to c times the distance between xk and x star. Okay, then the limit, which is sort of the lim sup as k goes to infinity of the distance of xk plus 1 and x star divided by the distance between xk and x star is called the linear convergence factor. The sequence and then an iterative algorithm on M is said to converge linearly locally linearly to a point x star if there exists a neighborhood u, okay, of x star and a constant again c in the interval from 0 to 1, such that the sum over every initial point x0 in this neighborhood, the sequence xk generated by the algorithm satisfies this contraction property. So I should say that, we had been talking a lot about Riemannian manifolds, and in particular we had talked about these geodesic normal coordinates which come from the exponential, and how, of course, in practice these are difficult to compute because oftentimes the exponential is difficult to compute, and so in many practical circumstances replace the sort of the exponential logarithms, etc., to these more cheaply computable retractions, and so it turns out that this notion of convergence, it's like which we've defined in terms of the Riemannian distance, can be actually also defined in terms of the retraction. Okay, so so let me just sort of make the remark that convergence sequence xk, right, on Riemannian manifold M, right, converges linearly to x star with constant C if and only if the following is true. That I'm going to write this in terms of the retraction now. So retraction centered at the limit point. Is less than equal to some constant times and of course, you know, it's like, sorry. Of course, that actually is going to be, it's going to be 0, right? Anyhow, so you might ask, well, why is it that you couldn't use a coordinate chart, but you could use the retractions? And more or less, it had to do with the fact that the retraction, if you recall, is at least, you know, in terms of the linearization, it gives the same linearization as the exponential, essentially, right? So so in essence, then, or actually, let me rephrase that. It's like the retraction. It's like the inverse of the exponential. So the linearization of the retraction is like the actually, no, sorry. The retraction is like the linearization of the exponential. It's like the linearizations agree with each other, and the exponential, of course, it's like is very closely related to the notions of geodesic normal coordinates. It's like and geodesic distances, and so again, it's not so surprising that at least when you're close enough to x star, it's like everything sort of works out the way you expect it to work out. Okay, so again, you know, it's like this would not be true in general. It's like if you had done this with coordinate charts, but the retraction maps have this local rigidity property. It's like which makes it so that you can use them. It's like and still have something which is well defined. Okay. Okay. So. All right. So let me say something about so superlinear convergence then. Okay, so let M be a manifold. Okay, and let sort of xk, k equals to 0, 1, and so on, right, be a sequence. Okay, so I should sort of go back and say this a little bit more carefully, right? So the retraction, as you recall, is a map from the tangent space, it's like to the manifold, right? And that's, of course, true, it's like with the Riemannian exponential as well. So So the way you get geodesic normal coordinates typically is to take the inverse of the exponential, which is of course the logarithm, and then it's like pick a basis, it's like on the tangent space, to convert that tangent vector now to an n-tuple of numbers. Okay, so if instead of the logarithm, right, the Riemannian logarithm, you take the inverse of the retraction, and then again you had chosen sort of a basis for the tangent space, then that would give you, of course, a coordinate chart, right? And that's basically what you're doing here, right? You have a point, right? The inverse of the retraction, it's like gives you a tangent vector, right? If you had chosen a basis, you get an n-tuple, and then it's like you could have defined it's like the norm, it's like on that, or you could have just directly defined the norm. It's like on the tangent space itself, okay, which is sort of what we're doing here. Okay, so again, it's like this is sort of the what you would normally expect, right? And of course, this other term here really is 0 because the retractions, inverse of retraction centered at x star, it's like applied to x star, it's just going to give you this 0 vector. Okay, so these are sort of 0, but I've written it there just to make it clear that you're doing something which is morally like the distance between xk plus 1 and x star here. Okay, all right. So, and of course, you know, we're going to see that, again, more generally on a manifold, it's like you have this kind of notion of a chart, which gives you this notion of superconvergence. Okay. All right. So, okay. So let M be a manifold, and then let this sequence be a sequence on M, right, converging to x star, then let U and let phi be a chart, right, of M with the property that X is in the domain of definition. It's like the chart. So if it turns out that the limit as k goes to 0 of the coordinate associated with xk minus the coordinate associated with x star, right, the norm of that divided by the norm of the coordinates of xk, so xk plus 1, right, was here, xk plus 1 and then xk, right, minus the coordinates associated with x star, right, that is equal to 0, then xk is said to converge superlinearly. To x star. Okay, if there exist constants say p greater than 0 and c greater than equal to 0 and k greater than equal to 0, such that for all k greater than equal to big K, there's this inequality that the norm of this is less than or equal to some constant times the norm to the p power, and we say that it converges at a particular rate. Then xk converges, is said to converge to x star with order at least p. Okay. And an iterative algorithm on a manifold M right is said to converge locally to a point x star, right, with order at least p. If there exists a chart. Okay, at x star, okay, and a constant c, such that for every initial point x0 in U, the sequence xk converges. Okay, xk satisfies the inequality, and okay, then if p equals to 2, right, we say that this convergence is quadratic. And if p equals to 3, convergence is cubic. Okay. All right. So, all right. So if you recall, it's like, we had earlier said that the notion of linear convergence depended on the chart. It's like, and so we could not use the chart definition to talk about linear convergence. So you might ask, well, why is it that here it's like we can talk about convergence for superlinear convergence, right? P greater than 1, for example. Okay. And the reason, if you will, is because what essentially happens is that this constant here would typically depend on the chart. Okay, and the reason why when we were using retractions, it's like we were able to use retractions but not arbitrary charts, is because the rigidity condition means more or less that when you're close enough to the base point, it's like of the retraction, the retraction behaves like the exponential. Okay, so leading order behaves like the exponential, and so this constant which you get from the retraction is the same constant you would have gotten, it's like from the Riemannian exponential and the logarithm. Okay, so but more generally speaking, it's like it could be anything. This c would have depended on the chart you have chosen. So so the important point is that this exponent here is independent of the chart, but the constant is in general dependent of the chart. Okay, but the notion of superlinear convergence, as you see, doesn't require that this constant be within sort of the interval from 0 to 1, which we had required in the linear contraction setting. Okay, so it just has to be some constant greater than or equal to 0, and then what really matters is sort of this exponent, if you will. Okay, so more or less the upshot, if you will, is that if you had looked at, you had done this, it's like in the linear space case, in the linear convergence case, that c would have depended on the choice of the chart, and in order for you to have linear convergence, that c has to be specifically between 0 and 1, and so you can't really make sense of the notion of linear convergence in a way which is independent of the chart. Whereas in the superlinear convergence case, what really matters is the exponent. The exponent is independent of the choice of the chart. And again, only this constant c is dependent on it, but there is no real restriction, it's like on what c is, except that it's non-negative. Okay? So, so that's the reason, if you will, why when we talk about superlinear convergence, we can do this in this chart setting, but we could not have done that in the case of linear convergence. Okay, and we needed something stronger. It's like a chart which was induced by a retraction. Okay. Okay. So with that, it's let me sort of just state some final general results about convergence rates. Okay. So again, we're looking at the case of these kind of fixed point iterations, right? So I'm going to consider maps of the form xk plus 1 is equal to f of xk. All right, then the following theorem applies to that. Okay, so let f be a map from M to M, be C1 mapping, and then whose sort of domain and range include the neighborhood of the fixed point. Okay, and I should say that these kind of iterations are what are called fixed point iterations. Okay, so this is a fixed point iteration. Okay. All right, so the following then, if the linearization of f at the fixed point is equal to 0, then the iterative algorithm with the iteration mapping f converges locally superlinearly. To x star. And the second thing is that if df x star is equal to 0 and f is twice differentiable, f is in C2, then the iterative algorithm with mapping f converges locally quadratically to x star. And I should say that in particular, it's like you can use this sort of fairly general result, certainly in the vector space setting, to prove, for example, that the Newton algorithm is sort of locally superlinear. It's like in general, but in particular, it's like it's like when you don't have multiplicity, that it's quadratically convergent. Okay, so. So this is powerful for smooth iteration mappings, but it's not very practical for sort of line search methods and trust region methods. So the remark is that this is very powerful for sort of smooth iteration mappings. Not useful, not usually useful for line search. And trust region methods. Because the step size selection is non-differentiable, right? So the theorem does not hold or does not apply because of the non-differentiability. Okay, so let me stop here for now.